All right. Good morning, everybody, and welcome to our webinar. Today we're going to be talking about supersonic aircraft shape design powered by Stanford's SU2 software suite and Pointwise for mesh generation. My name is Travis Kerrigan. I'm a senior engineer here at Pointwise, and my primary responsibility is to work with clients to help strengthen their CFD process by developing either interactive or automated meshing solutions for them using our software. I'm joined today by Thomas Economon. Tom is a PhD candidate in the Aerospace Design Lab at Stanford, and his research focuses on the development of design methodologies for aerospace systems, including adjoint-based techniques like those he'll be talking about today, as well as optimal shape design. Tom is also a member of the development team for the open source SU2 software suite. So thank you for joining us, Tom. We're also joined by Dr. Francisco Palacios. Francisco is an engineering research associate at the Department of Aeronautics and Astronautics at Stanford. And his research includes optimal shape design, large-scale multi-physics CFD calculations, numerical analysis, and algorithm development. And Francisco is also a member of the development team for SU2. And lastly, we're joined by Trent Lukacek. Trent's a PhD candidate in the Aerospace Design Lab at Stanford, and his core research interests include aircraft design and optimization, and he's working on contributing to the design of NASA's next-generation supersonic passenger jet. He's also a member of the SU2 team. So thank you guys for joining us today. So before we get started, I just wanted to introduce the geometry and the topic that we'll be describing today. As you can see up here on the screen, the geometry that we'll be working with is the Lockheed Martin 1021. This was developed for NASA's N+2 supersonic validation program. It's a low boom design, seats about 80 people, cruises at Mach 1.7, so a little slower than the Concorde, but the benefit here is it's a low boom design, meaning it can fly not over water, but over land supersonically. Okay, it doesn't have to slow down as it comes over the continental U.S. This is also the geometry that was used as part of the first AAA sonic boom prediction workshop. And really the goal with a lot of those AAA workshops is really to assess the state-of-the-art in computational technology, and for this particular application, for predicting boom signatures suitable for sonic boom propagation to the ground. Okay, so as you'll notice from the geometry on this screen, something a little bit different. We've removed the wind tunnel arm, and we're simply working with the aircraft surfaces themselves, because we're going to do a little bit of optimization. So while we're going to describe some of the best practices for generating the meshes that came out of the Sonic Boom Prediction Workshop, we're also going to be talking about how you can do optimal shape design. And so our goal is to minimize the drag subject to a number of aerodynamic constraints, things like lift and pitching moment, etc. Okay, so with that, why don't we get started talking about the pre-processing. The first step is importing the geometry into Pointwise. Okay, so Pointwise we'll be generating the mesh using the software and cleaning up the geometry. We can bring in native CAD. As you can see in the first image on the top, we have the CAD geometry consisting of a number of surfaces. Each surface is colored a different color so you can see them. And through our solid modeling technology, we're able to take this geometry, turn it into a watertight model, a representation of the aircraft that is watertight, that consists of a number of what we call quilts or logical meshing regions. And really what this allows you to do is kind of structure up your mesh topology, your surface mesh topology, prior to even putting the surface mesh on the aircraft. Okay, and we're not going to talk too much about this because we've discussed this in previous webinars, but this is the point at which we'll be starting with the watertight model, all quilted up, ready to go. And at that point, we can simply grab that model and automatically put a watertight surface mesh on it. Okay, so enough with this slide. Why don't I jump into Pointwise and demonstrate that? So here's the aircraft. Again, watertight solid model, all quilted up, ready to go. And I'm going to put an unstructured surface mesh on it. Just to let you know, it's going to be a relatively isotropic surface mesh. Okay, this is for an Euler calculation, which happens to be a good enough assumption for these high-speed flows like this Mach 1.6 flow in the cruise configuration, really where the inertial forces are going to dominate the viscous forces. So what I'm going to do is I'm going to specify some defaults for the entities that I'm about to create. So I'm going to create a couple different types of entities, the first being a connector. A connector is our terminology for a grid curve, contains grid points, and then I'll be creating unstructured domains. So those are triangular surface meshes. Okay. And before I do, I set up defaults. And what this does is that any entity that I create from now on is going to have these attributes. All right. This is really nice because what this allows us to do is set the problem up beforehand and get 90 to 95% of the way there with the surface mesh. And then after the fact, we can begin to modify those entities. So this is really important, is we have the automation of easily putting the surface mesh on there, but we can always back out and get the control that we need by adjusting the attributes of these entities after they've already been created. Okay. So the first thing I'm going to do is I'm going to specify an average grid spacing of 1 millimeter. All right. This is a grid spacing that works for some of the largest components of my geometry, like the wing or the fuselage. And when I say works, I mean it's going to give us a triangle size that accurately captures the geometry in those relatively large regions. Okay. The next value I'm going to change is the maximum dimension, and this is basically just to ensure that we don't exceed the number of grid points on a given connector, because there are going to be some very long connectors that are created as part of this process, and we want to ensure that we don't exceed the number of grid points. Next, I'm going to set a maximum angle value of 30 degrees. What this is going to do is it's going to ensure that the turning angle on a given connector, if you think about it, a grid curve contains grid points, it's discrete, so it's going to look at adjacent facets in that connector, adjacent segments, and ensure that the turning angle doesn't exceed this value. And if it does, it's going to increase points so we get nice smooth transitions in areas of high curvature. I'm going to skip over maximum deviation. You tend to need to know a little bit about your geometry before using this. So I've elected not to use this geometry. It simply looks at the deviation from the underlying geometry to insert points. But I am going to use this, use surface curvature. So I've enabled that. What that option does is if we create a connector that runs, for example, the span of the wing, okay, there's not a lot of curvature in that direction. However, in the transverse direction there is. I mean, that's the leading edge. There's a lot of curvature. And so what use surface curvature will do is it'll look at the geometry in the transverse direction and insert points on that connector so we can get a nice smooth transition from those domains to the connector. All right, so now for unstructured domains, the first thing I'm going to do is I'm going to change my algorithm type from Delaunay to advancing front. If you create a Delaunay mesh or an advancing front mesh and you bring them into the examine tool and look at their quality, you're probably not going to see much difference between the two. But what you are going to notice is, for one, the advancing front mesh looks a little bit nicer, a little bit cleaner. The other thing is this body consists of several cylindrical shapes, the nacelles, the fuselage, the nose. And what I've found is that advancing front does a better job of more regularly capturing those geometries. So that's why I've elected to use advancing front for this case. Boundary decay, I'm going to increase that to 0.85. And what that does is it slows the growth from areas of tight clustering to areas that are relatively coarse. So it's going to smooth the transition. Next, I'm going to change my maximum edge length, basically capping the size of the triangles and relatively flat portions of the geometry. And then lastly, increase my maximum angle to 30 degrees. Again, this will be kind of used in conjunction with some of the connector defaults and allow for nice smooth transitions in cell size on the surface mesh. All right. So at this point, I'm done. I encourage you to kind of play with some of these parameters in Pointwise. Again, you don't have to worry because you can always adjust this after the fact. Okay, so you can select your entities after they've already been created and modify their individual attributes. Okay, but what this does is it allows us to select that model, ensure unstructured is picked in the toolbar, and then you can click on this button that says Domains on Database Entities, and that will create a watertight surface mesh for the aircraft. Now that operation takes about a minute or two, so I've already created that. I'm going to pull it right up, save a little bit of time. So here's what you would get after you click that button. Okay, so as you can see, it's pretty smooth surface mesh. Again, it's isotropic, consisting of triangles. And at this point, you would begin to modify or potentially refine the surface mesh till your heart's content, until you're satisfied with the resolution that you're getting for the geometry in the surface mesh. One area I wanted to point out is here at the nacelle lip. You can see that turning angle on the domain level is used to insert points, so we get nice wrapping around that nacelle lip. And then this connector, that use surface curvature option, has inserted additional points into that connector, so we get nice smooth transitions in the transverse direction. Okay. So again, a great way to get almost all the way there, and then you can begin to modify and get it to the point where you're ready to start volume meshing. So that's the next step, creating the volume mesh. Now for this case, we've elected to create two blocks. A block is our terminology for a volume mesh. Okay, we've created two blocks. We've created an inner tet core and then an outer hex far field, kind of in this cone shape. Okay, and what that allows us to do, that inner tet core gives us a lot of flexibility, a lot of freedom to do things like adding components to the geometry. We can automate it using our scripting language. We can change the angle of attack. We can do all sorts of things when we have this tet core. The other thing we can do is we could easily convert this to a viscous block using our T-Rex viscous unstructured meshing algorithm. Okay, so again, we got a lot of flexibility when we do this. The reason we've elected to use this Mach-aligned hex far field is because we've actually found, it's been shown that Mach-aligned hexes yield results that are often superior to those that come from adaptation or refinement schemes, especially the farther you move away from the actual vehicle at lower computational cost. Okay, so we can compute the Mach angle for the cruise configuration and get an idea of how to shear these hex elements in the far field. And what you'll find when Tom starts talking about the results is that we get great shock persistence well into the far field. So if you wanted to extract pressures a number of body lengths away from the vehicle, you could easily do that, and great Mach contour alignment. You'll notice that we capture those shocks pretty sharply. Okay, so I'm going to show you how we can do this in Pointwise. Okay, so here is my completed surface mesh, all cleaned up, ready to go. Really what I would want to do at this point is create my far field geometry, and that's exactly what I've done here. So we don't have to go back to CAD to do this. Pointwise has some tools for creating geometry. We can create B-spline surfaces, ruled surfaces, we can do revolves, things like that. So you can create the far field geometry in Pointwise. So here's a great example. Maybe we draw this curve. We could do a revolve. And you'll notice we get this nice surface of revolution. And then the idea is that we create all these surfaces, create the curves, create the surfaces. We can assemble our model and then put a surface mesh on those models very, very similarly to how we did that for the aircraft. And then we can create the volume mesh for the tet core and then the hex far field. Okay. So I'm going to turn on the tet core, and we'll zoom in here and take a look at it. So I'll grab that. Turn off the view of the domains and then sweep this through to a more interesting part. Okay, something like that. And you can see, again, it's just an isotropic far field for this Euler calculation. Great quality. But the thing, I really want to point out is this gives you a lot of flexibility, a lot of freedom. We can add things to the geometry and that sort of thing. It's easy to automate, so we could pretty much script this entire process for creating the volume mesh and that far field geometry. But again, the other thing is if you're satisfied with the surface mesh resolution, okay, the way that you're capturing the geometry, you could easily convert this to a viscous block by bringing it into T-Rex, specifying things like your number of layers, your growth rate, some quality constraints, your initial delta S, given a target Y plus value, etc. So then you can just reinitialize the block, and you've got a viscous block out of it. So you really do have a few options by going this route. All right, let's turn the domains back on, and you can see really the interface between the structured and the unstructured is this this quad region, and the element, the transition element between the hexes and the tets would be a pyramid. Okay. All right. So the next step is the creation of FFD boxes. These are free-form deformation boxes, and Tom's going to talk a little bit about these as well, because these are for SU squared. And really the primary responsibility of these boxes is to define the regions for shape deformation. Okay, so these provide the mechanism for doing shape deformation in SU squared. All right, and what's required are the 8 corner points of the box as well as the IJK polynomial degree for the deformation. And traditionally, what's been done to create these, you would go maybe go back to CAD, pull in your geometry, and figure out where these boxes should lie, maybe approximate some of these points and that sort of thing. And then you'd append this to the bottom of your SU2 grid file. But what we've done is we've actually written a script in Pointwise that allows you to create these boxes within Pointwise and export this data to the SU2 file. And it doesn't only work in 3D, it also works in 2D. So the recent version of SU squared supports 2D FFD boxes. Tom's going to talk about that as well. And the script will allow you to create both 2D and 3D freeform deformation boxes. So I'm going to demonstrate that. Okay, so here is my aircraft again. Note that I'll let you know that the script will be available as early as tomorrow. I encourage you to look at the header of the script. There's a README. It describes kind of how the script works, how to use it. But probably the biggest thing to note is there's no GUI with this script. There's no TK interface. It's driven all through groups. Okay, and groups are great because they provide a mechanism for doing selection. Okay, and so you can create a group of domains. For example, when we're creating these boxes in 3D, we would create a group of domains. We would create a box around these domains and scale it, okay, give it the appropriate dimensions, and then we could export that as an FFD box. Now, there's actually an entity type in Pointwise that has all of the information necessary for doing this, and that's a structured block. A structured block has 8 corner points. It has an IJK dimension, and so that's what we use to actually gather the information necessary for creating these boxes. All right. So how do we go about creating these boxes in Pointwise with the script? Well, the first thing you have to do is you need to create what I call FFD groups. And an FFD group consists of 4 things. The first being FFD. Okay, FFD defines this group as an FFD group, followed by the name of the FFD box, followed by the scale vector for the box, as well as the IJK polynomial degree. Okay, once you have that, you simply execute the script. The script will run. It will create the boxes. Okay, so you can see it's created the boxes, and it will convert the FFD groups to FFD layers. Now, this is really nice, the fact that they're tucked away in layers, because we can toggle them on and off. So I can turn them all off. And this is great because if you have a lot of these living in the display at once, you can toggle them on and off to kind of declutter. You can do things like selection is another great thing. So for example, I can grab all the wingtip domains and zoom to selection, okay, zoom right into those boxes and begin operating on it, okay. Excuse me. So one thing I should probably note, as you notice from that box on the wingtip, is that these boxes are aligned with the global XYZ axis, okay. They're not necessarily aligned with the geometry. So what we do is we create database points, and so you'll notice these pink points that have been created. Those are database points, and you can use those as anchors for various transformations in Pointwise to allow you to transform the box to more appropriately conform to the geometry that you're enclosing. And this is going to allow for a more accurate shape deformation in SU squared. So why don't we go ahead and do that. I'll grab this domain and go Edit, Transform, Stretch, and I'll pick my anchor point. I'm going to go from this point, and I'll just say we're going to restrict it to the body X direction, and go there. Okay, so we've moved that. I'll do the same thing on the opposing side. Edit, Transform, Stretch. I'll repick my anchor. So that'll be my anchor point. Again, I'll just restrict myself to moving in the body X direction. And so now I've basically transformed that box to more appropriately encompass that wing tip. Okay, and this is going to be very similar to the box that Stanford used for the optimization. Okay, so at this point, we're ready to export these boxes to SU2. So the way to do that is you simply execute the script one more time. So what will happen is it'll ensure that all of the FFD groups have been converted to FFD layers. And then once that happens, it will write out all the data. So if we take a look, it actually writes, apologize, it actually writes an ffd.su2 file. And if we look inside there, you'll notice all of the FFD information is available. The nice thing is once you write out the grid, you can simply concatenate these two together and then pass that off to SU2. All right, so the last step is exporting the mesh. And Stanford's been nice enough to provide us with a plugin for SU2 that shows up in Pointwise as one of the supported solvers. And it allows you to create the grid, assign your boundary conditions, and then export the mesh to the native.su2 file format. All right, so we'll go ahead and show that. So the first thing you'll want to do is turn off your FFD boxes. Okay, so why do you want to do that? Well, those are actually grid entities, and we don't want them going out with the mesh. All right, they were used solely for the purpose of defining the FFD box. We've already exported them, so we just need to turn them off. I'll turn on my far field. Okay, so what we want to do is we want to go to CAE, select solver, ensure that Stanford's SU2 has been selected. We'll then go to CAE, set boundary conditions, and we're going to set 3 boundary conditions. Okay, the first one being the aircraft, the second being symmetry, and the last being far field. Okay, so I'll grab all of the aircraft domains, put them in that boundary condition, grab the 3 symmetries, put them in that boundary condition, and then last I have 5 domains that are unspecified. I can simply add to selection and drop them into the far field boundary condition, and then we're done. Okay, so these are the boundary conditions, the tags that you'll actually use in the configuration file when you're setting up boundary conditions for SU2. Okay, so at this point, we would just grab the 2 blocks. Okay, so I've grabbed the inner tet core and the outer far field, and go File, Export, CAE, and then we would export the grid data to the .su2 file format, and then simply concatenate that with the ffd.su2 file. And that's the information that we would pass off to SU2. Okay. So with that, I'm going to pass things over to Tom, and he's going to begin by talking about how to configure SU2 to solve the Euler and adjoint Euler equations and retrieve the surface sensitivities that drive this shape design optimization problem. So Tom, I'm going to give you control. Okay, you should have control.
Great, thank you, Travis. So it's my pleasure today to introduce you guys to SU2 and how we do shape design in SU2. So first, what is SU2? So a little bit about it. It's an open source suite for CFD, shape design, and a lot more. Today we're just going to talk about aerodynamic design, but we can also do multi-physics calculations, we can do low boom design. We have a number of other capabilities that we won't get into, just given time constraints. So this is an industry standard type of tool with industry standard numerical methods on unstructured grids. And it's mostly object-oriented C++. We use a lot of Python scripts for automation, and we're going to show quite a bit of that today. And so as Travis has just done for us, he's put together a nice baseline geometry and mesh. And once that's available, we can go ahead and use SU2 to analyze the performance, evaluate sensitivities, and go ahead and perform automatic shape design, which will be the example that we're going to show today. So one of the key features I want to point out in SU2 is the availability of gradient information, so sensitivities. This is one of the key features. It's built right in. We're going to take advantage of that for our optimization today. And another thing is that everything you see here is in SU2 version 3.1, and that's available now for download. I encourage you to check out the website here. And there's a lot more information and training on how to build the code and install. We won't have time to go into that today. So we'll assume that you've got the code downloaded and built, and check out much more of the materials online. So let's talk a little bit about optimal shape design in general and what some of the tools are that we need to perform the optimal shape design loop. So given the nice baseline geometry and mesh that Travis created, that's going to be our input to the shape optimization cycle. So we're going to need several tools. First is something to perform geometry parameterization. So Travis alluded to this. This is what we call freeform deformation. We're going to use those freeform deformation boxes to control the surface shape of the geometry. We're also going to need a tool to deform the volume mesh. So once you've changed the shape of the surface, we need something to deform the volume mesh. And we're going to solve the linear elasticity equations to do that. Then we need tools to evaluate the performance, so just the analysis. And we need to be able to compute gradients. So the key here is we're going to be picking an objective function, something like lift or drag, moments. We're going to call that J. So we need to be able to compute that value and also get the gradients of that value with respect to a set of design variables, x. So these are our FFD control points. And so we're going to be using SU2, the finite volume unstructured CFD solver, and adjoint solver. We'll talk a little more about the adjoint solver later, to compute both J and the gradient of J. So compute the drag, for instance, and also the gradient of the drag with respect to our FFD control points. And this whole thing is thrown in a loop. We're going to let an optimizer drive this process, so continuing to change the shape of the surface, deform the mesh, compute the performance, compute the gradients, until we converge on some optimum value for J and the design variables, so the FFD control points X. So that seems like a complicated process, and it is. There are a lot of moving parts. But the beautiful thing about SU2 is that we provide everything you need for that shape design loop. And so you're going to configure each of the modules, each of the C++ modules within a single config file, and these carry a .cfg suffix. And we're going to let Python go ahead and drive this whole process for us. So once you've configured your options in the configuration file, you're going to go ahead and call shape optimization.py. And this script will automate the entire shape design loop for you. So here's an example of the call you might make to redesign this Lockheed Martin case, which we haven't talked exactly about the problem yet, but you just go ahead and make a call. You give it the config file, and in this case we were running on a cluster, so we said run it on 96 cores. After that, Python is going to go ahead and take over. It's going to call our C++ modules, compute the flow and the adjoint, and deform the surface and the volume mesh, and run the whole design loop for you. And one of the key ideas here is you can usually adapt an existing config file from an existing case to your needs. And to talk a little bit about the problem we're posing today, we want to pose a realistic shape optimization problem for this complex supersonic configuration. So the specific problem we're posing today is to minimize the drag. And so this is the objective function that's going to drive our optimization process. We're going to impose some aerodynamic constraints. So we're going to decrease the pitching moment by 25%. We want to maintain 95% of the original lift. And we're also going to impose some geometric constraints, so some thickness constraints at 5 different sections of the wing, so 5 different cuts. And we're going to want to maintain 90% of the original maximum thicknesses. So it's kind of a minimum thickness constraint, really. So we know that it's going to be difficult to reduce drag given a good starting configuration based on supersonic theory, which this configuration that's the case. So our problem essentially is to trim the aircraft. So we're going to change the wing shape using our FFD control points during the design, and we're going to try to reduce the pitching moment and trim the aircraft. So with that, though, there are a lot of things that are going on under the hood in SU2 that we want to give you a little bit of detail on so that you know how to set up your own shape design problems and what types of things you need to know that SU2 is doing under the hood. So first, let's talk a little more about geometry parameterization. So as Travis showed you earlier in the demo, we're going to use freeform deformation boxes to change the shape of our surface. And so this has origins in the computer graphics industry. The idea is that we want to define these FFD, these bounding boxes around our surface geometry, and we're going to create a mapping between the control points, so the FFD control points, which are the the intersections of these lines on the outer box here you see around this wing. And we're going to create the mapping between those points and the surface mesh nodes. And once we do that, we can then, for instance, grab some of these FFD control points and move those around, and we'll find that the surface inside inherits a smooth deformation. So the simple example I'm showing here is the on our M6 wing, and we're going to go ahead and pull those 4 FFD control points near the tip upwards, and you see that the wing inherits the smooth, large deformation. As Travis mentioned earlier, we have FFD control point variables excuse me, available in both 3D and 2D now with version 3.1. And Travis has shown you a new script that can generate these for you very quickly and easily in Pointwise. So once you have that information from the Pointwise script, for instance, that looks like the information on the right you see. So this is going to define our FFD control box. In fact, this is the specific FFD box that we're using for the Lockheed Martin problem. You're going to go ahead and take that information and append it to the bottom of the SU2 native mesh file. And once you do that, you'll notice that at the bottom, the control points and surface points, those are equal to 0. We need to initialize the mapping that I mentioned on the last slide by running the SU2 MDC tool one time with a configuration option dvkind equals FFD setting. That's going to go ahead and compute this mapping for you and write a new copy of the SU2 mesh with all of the FFD information inside of it. And we're going to write that to disk, and then this is the new mesh that you're going to want to use from that point forward during the shape optimization process. To show you the specific box we've set up for this case, this is the FFD box out by the wing. We're going to be designing the outboard section of the wing, and we're going to be using 264 of these FFD control point variables. So we can use a large number of variables, and this is one of the nice features of the adjoint methodology we're using, is that we can compute the gradient for a large number of design variables very efficiently. So this is the view of the FFD box that we're going to be using for design today. So we've talked about the geometry parameterization. We also need a way to deform our volume mesh inside the design loop once we've picked a new surface shape. So we really want a robust mesh deformation technique. And what I mean by that is once we change the shape of the surface, we want to be able to deform the mesh robustly so that we don't have any negative volumes. We can't allow the optimization process to fail. So the way we do that in SU2 is by treating the mesh as an elastic solid, and we assign non-uniform stiffnesses to all the elements in the volume mesh. We then solve the linear elasticity equations on the mesh, so at all the nodes, to get the nodal displacements, and we use the movement of the boundaries as the input. So another simple example here, I have just a nice brick mesh. It's a RANS type mesh, so we have tight spacing down near the wall, the gray surface. And what I'm doing is defining an FFD box that isn't shown, but I'm pulling a control point upwards and making a large bump deformation in the bottom surface. And then we're deforming the volume mesh around it. And you see the result is a nice smooth volume mesh that inherits the smooth shape of the boundary surface, and we keep high quality near the boundary. To quickly highlight some of the options, in particular one, for the mesh deformation tool is how we compute these stiffnesses. It's an important choice. So we can do this, we typically do it in one of two ways. We either use the inverse of the cell volume to set the stiffness. So that means that if you have a RANS mesh like you saw on the last slide, you're going to have cells with very small volumes near the wall. We basically want those cells to move rigidly under deformation to keep high quality, maybe in your boundary layer, for instance. We can also use wall distance similarly. So if you have tight spacing near the wall, those cells will also have a high stiffness, which will deform more rigidly, and that will also help maintain high quality near the wall. So then we need to move on, and we need to actually compute the flow and the adjoint. And so for this, we're going to be using SU2, the unstructured meshes inside of SU2. The schemes we use are median dual control volume based, so vertex based schemes. We're going to be using the finite volume method with industry standard second order schemes, so centered schemes, upwind schemes. And for this particular problem, we're going to focus on using JST in spatial integration, so a centered scheme. And in time, we're going to be using an implicit scheme. One of the nice features of the continuous adjoint that's in SU2 is that it results in a continuous PDE that we can go ahead and solve using a lot of the same or at least similar numerical methods to the flow problem. So we can reuse a lot of the machinery inside of SU2, a lot of the object-oriented class structure we can reuse to solve both the flow and the adjoint problems. And there are some small modifications that are important, but the idea is that we can reuse a lot of the structure. So we've talked about the key features that we defined earlier in the shape design loop. So we have the geometry parameterization, we have mesh deformation, we have the analysis and the gradient, so we compute the adjoint in order to get gradients. And so as the designer, you need to finally set up what optimization problem you want to solve. And so I mentioned what we're doing earlier for the Lockheed Martin problem. And you need to go ahead and pick your objective, any constraints, so including geometric constraints like wing thicknesses, and you want to specify the design variables you've chosen. We have a lot of options for this in SU2. We're just going to show a handful today. And you can go ahead and find the whole list, so a pretty comprehensive list, inside the config template.cfg file. And this can be found in the home directory, the root directory of the source distribution. What you'll see if you open up the config file for the problem that we're showing today is at the bottom you're going to find a section where you set up your optimization problem. So we have the optimization objective, so this is drag, and we impose a scaling factor, and this is basically just to help the optimizer take an appropriate first step in the process. You also are going to impose some constraints. So here you can see we're imposing a moment y constraint, so this is to set it to be less than 25%, or a 25% reduction rather, in the initial value. We have a lift constraint to maintain over 95% of the original lift. And then we have a number of maximum thickness section constraints. So for 5 different sections of the wing, we are requiring that the thickness remain above 90% of the original thickness. Lastly, and very importantly, we have the definition of the design variables at the bottom. And so if you look at the file that we provide for this case, you'll see that there are 264 FFD design variables at the bottom. And each one of these specifications in parentheses is an FFD control point variable. And so there's a tag like this for other types of design variables as well. I encourage you to check out the config template file to see the actual specification. But the key idea is that each one has a tag number. You're going to tell it which markers. So as Travis showed you, the aircraft in the mesh is named aircraft. And then it's going to have a number of specifications, such as for the FFD control points, it's basically a structured mesh, so you have an IJK index for each point, and it can move in the X, Y, or Z directions. So we're basically allowing this particular control point to move in the Z direction. And you're going to go ahead and list all those out with semicolons separating them at the bottom of your config file. So now that we've talked about all the pieces, we're going to come back and you're going to make that call to shapeoptimization.py, and we're going to feed it in the config file that we've prepared, and we're going to run it on 96 cores. And this process is going to take a little time, so you have time to step out and get a cup of coffee. We encourage you to pull down the Lockheed Martin file, the lm1021.cfg, and look through some of the options. We just don't have time today to go through all the specifics. We also have a lot of these options explained on the website, and a lot of material, and a lot of other example config files that you can use to build off of. And while this is running in the background, you're going to find that it creates some folder structures for you to store the results. There's going to be a file called historyproject.plt that's going to have the optimization history in it. So it's going to create and organize a lot of output files for you. So to move on, just to show you the final results, we've pre-computed this. And we're going to go through some of the results and talk a little bit about what SU2 will give you in terms of outputs. So first, just to highlight, while we're not talking about low boom today, or low boom design, we did, as Travis showed, set up this mesh to help with low boom type predictions. So this is a cut of the symmetry plane, and we're looking at mock contours. And the idea was that these shock-aligned hex cells, these Mach-aligned hex cells, are going to help maintain accuracy and reduce costs for boom predictions, which usually requires you extracting off-body pressure signatures, some number of body lengths below the aircraft, for instance. So we want these shocks to persist down toward the ground, and we want to help maintain that accuracy for these boom predictions. So you can see that this mesh lends itself well to that. To spend another moment, if we talk about the continuous adjoint and what that is going to provide for you. So each time the shape optimization process requires gradients, it's going to go ahead and call the continuous adjoint functionality in SU2. And when it solves the continuous adjoint PDEs, the result is something that we call the surface sensitivity. So this is a measure of the change in the objective function at each node on the surface due to small perturbations in the local normal direction. So in this case, for a particular objective, here we're showing drag, we're plotting the surface sensitivity on the surface of the body with respect to small perturbations. So this sensitivity map is saying if you were to take one of these surface nodes and perturb it just a little bit in the local normal direction, what is the effect on the objective? What is the effect on the drag in this case? Now these sensitivity maps are nice for a number of reasons. First, you can get some designer intuition. So this can show you where on the surface your geometry is sensitive to changes for a particular objective. This can also help you set up your design variables. So this might inform where you put your FFD control points, for instance, where on the wing or near the nacelles you might want to move your FFD control points in order to perform further design. And lastly, while we compute these surface sensitivities, in order to continue the shape design process, we need to project this information into our design space made up of the FFD control points. So SU2 is going to do that for you with another module called SU2 GPC. We're going to take this information at all the surface nodes and project it into our FFD control point design space in order to compute a new set of the design variables X. So let's look at the actual optimization results a little bit. So first, the objective and flow constraints. So what we're showing here is the CD with the optimizer iteration on the left, and we're showing the lift and the moment coefficients on the right with optimizer iterations. And we see that after our design process, after 8 iterations, we're satisfying both the lift and moment constraints, and we've achieved a smaller drag coefficient, just slightly, about 3 drag counts, but we knew it was going to be a little bit difficult to reduce the drag given a good starting configuration. So we're very happy with the results at optimizer iteration 8. But let's look a little bit at the geometric constraints. So we find that if we look at the results at optimizer iteration 8, it turns out that one of the sections near the inboard bound of the FFD box has actually increased in thickness quite a bit. And this is something we wouldn't expect. So we'd want to really go back and impose a new geometric constraint in order to constrain the maximum thicknesses, because remember, we only constrain the minimum thicknesses. So this is something we would want to go back and do in a subsequent iteration of this design process. And we'll talk a bit about that later. But from here on, let's take a look at optimizer iteration number 3. So this result looks actually pretty promising. So if we take a look at these section cuts over here on the right, we're showing these 3 different cuts of the wing from the baseline geometry to the 3rd iteration of the optimizer, and we're showing the shape changes locally for each of those sections. If you take a look at the pressure coefficients now, this is for the upper surface of the aircraft. We have the original on the upper portion and the optimized version on the bottom portion. There are a couple things to point out. First, you can see some artifacts of the removal of the sting. So we weren't including that in the optimization, but you can see there is a small artifact of the sting, or at least the old portions of the sting where it was removed. And remember that we put the FFD box around the outer portions of our wing. So if we look at the pressure contours in the outboard sections, we find that on the optimized version, we've actually made the pressure coefficient less negative. And if we go ahead and take a look now at the bottom surface, we're going to find that now the optimized version is on the top. We're going to find that we've actually increased the pressure in the outboard sections, especially near the back, near the the trailing edge of the wing. And we've also changed some of the characteristics of the shape, the shock a little bit. So the shock coming off the nacelle near the outboard section of the wing has a slightly different shape in these results. If we go ahead and take the original and the optimized geometry, and here we're showing a close-up of the outboard wing section. So in gray we have the original geometry, and in green we have the optimized geometry. We find that the optimized geometry has actually lowered the leading edge slightly and also the trailing edge. So it's essentially introduced some more camber to the design. So as I mentioned before, we really have just gotten started on this problem. So we imposed a very kind of sophisticated optimization problem for this complex geometry. And we found that we were able to meet our objectives, but as designers, we would want to go ahead and take the next step. And we can do a lot of things at this point. So SU2 has a lot more features that you can play around with. And it's also important to highlight that, you know, these results, the automatic shape design is just a tool. And the designer is going to go ahead and want to impose more constraints or change the optimization problem a little bit in order to get a good final result. So there are a lot more things you can do. I'll just highlight a couple. One is you can go ahead and add more geometric constraints to the wing, for instance. So like we pointed out, we may want to go ahead and add some maximum thickness constraints to the wing. You may want to consider angle of attack during optimization. So rather than making these large-scale changes to the wing in order to trim the aircraft, you may want to change the angle of attack and make smaller changes to the wing. And lastly, we can make a lot of changes to how we set up the design variables. And this is made even easier now with the new Pointwise script that Travis showed. So some things, for instance, we might want to change the box, the shape, move the box around, add more control points, hold some of them fixed near the inboard section. We may want to try a different type of variables. So rather than control points, we have camber and thickness design variables that you can try. Maybe insert more FFD control boxes like Travis showed, or even nested FFD boxes. So you can have finer control in local regions, maybe near the nacelles or near the leading edge of the wing. So a lot of things you can try in SU2. And then lastly, once the designer is happy with the final result, inside of SU2 MDC, one of our tools, you can export an STL file of the geometry and reintegrate that with your CAD or manufacturing process. So with that, that's SU2, and that's how we do shape design in SU2. And thanks you for joining today, and I'll turn it back to Travis.
All right. Thank you very much, Tom. Okay, so the grid file, I'll just let you know the recording of this webinar, this presentation, grid file, script, solution, all that's going to be made available. So everything that we showed today will be made available to you as early as tomorrow. The links are below. You can see we'll post them on our website as well as on Stanford's website. We'd really like to acknowledge the NASA M+2 Supersonic program and Lockheed Martin for this geometry, being able to use this geometry. If we don't get to your questions today, if you have any questions regarding Pointwise, please feel free to email me. And if you have any questions regarding SU2, please feel free to email Tom, and our addresses are there. And I'll leave this slide up for the duration of the Q&A session. So with that, again, thank you all very much. We will open it up for questions. If you have a question, just feel free to type it into the questions dialog box, and I will pass them out. So it looks like we have a few questions already, so let me, and more coming in. Okay. The first question we have is there a link to referred previous webinars for watertight models? I have your name. I will contact you following this webinar and give you some links. But yes, if you go to our webinar page, pointwise.com/webinar, there's a link in the corner for webinar archives, and there's a number of webinars that we clean up the geometry. I believe even the second one is one where we're cleaning up geometry. Okay, let's see. Another question is, which optimizer is used?
I see. I can go ahead and take that one. So
yep.
Inside of SU2, the Python script that I showed you calling shapeoptimization.py, that's going to go ahead and call the SLSQP optimizer inside of the SciPy package, which is just one of the packages you can download for Python. It's a scientific application package, and they have some optimizers available in there. So we can do constrained optimization problems using SLSQP. Yes.
Okay. And there's two questions. So one is, can alpha be a design variable? And it looks like it can be. That's one of the points on your last slide. And what angle of attack was this calculation run at?
So this calculation was run at 2.1 degrees. So this is the conditions you'll find in the config file. Again, we invite you to pop that open. I didn't have time to go through that today. But this is the typical case that they propose on the website for the low boom. So I think it's Mach 1.6 and alpha 2.1. So you can go ahead and check that out. And yes, we do have the capability to do angle of attack changes. Mostly we do this by putting an FFD box around the entire aircraft and letting it deform the whole body, so move the whole body to change the angle relative to the free stream. So we've done this in the past, yes.
Okay. Let's see, a question. Can you post this online or in an email? Absolutely. Again, this slide will show you where all this will be. The recording and everything will be made available online, and on YouTube you can watch it. Okay, number of points in the mesh and the time it took to compute 8 design cycles. I believe there were 5 million elements in this mesh, and how long did it take to compute?
12 hours.
Yeah, we were running on 96 cores. It was about 12 hours to do the full design. Now, one thing to point out, I guess I'll take this chance, is if you're doing a steady problem like this, you can fully converge the flow and the adjoint problems, and you'll have adjoint problems for each of the constraints as well, which I didn't get to talk about that either. But you can converge these problems and just restart, so you can actually save a lot of computational effort. You just start from the converged solutions, and you just have a smaller amount to converge. But yeah, on the order of 12 hours.
A lot more simulations, so you have adjoints.
Yeah, so you're running a flow. I guess I should be a little more clear. With each shape optimization, well, with each step of the major step of the optimizer, you're going to compute a flow problem, an adjoint for the drag, an adjoint for the lift, an adjoint for the moment, and then we also have to evaluate the geometric constraints, which are cheap. They're very cheap. But so that process, with each loop, you have quite a few solutions to calculate.
Okay. That kind of leads to another question. Why only 8 iterations for the optimization?
Yeah, so we found that inside of the optimizer, what we weren't showing is that it's taking a lot more steps than we showed. Those are the major iterations of the optimizer. And indeed, if you wanted to go all the way to a full converged, a local optimum, let's say, you may need to do something on the order of the number of design variables. And that's true. We find that as the designer, you kind of need to watch this process, and once you've decided that it's either more or less converged or it's not changing much, or you've reduced whatever it is you're interested in reducing, that you've made it a better design. But mathematically speaking, you would want to go all the way to a local optimum, which you can. We just chose not to go that far because again, these are expensive. These are large cases.
Okay. All right. Here's another question. How do the surface sensitivities compare with those computed from discrete analytic methods and the finite difference method?
So this is a common question. This comes up all the time. So there are a number of answers to that question. So the first thing to say is the finite difference and the discrete adjoint methodologies are going to give you what we call numerically exact gradients. So they are they kind of match up exactly with what numerically is in the code. So basically you have the discrete algorithms and you're basically taking the derivative of the discrete algorithm. So in terms of numerical exactness, you do get that. The continuous adjoint, on the other hand, offers you quite a bit of flexibility in that you're solving another set of PDEs, and you can solve it with a similar type of numerical method as you do the flow problem. And so you may mathematically say that you're solving a more physically intuitive or a more physically appropriate problem to get the gradients rather than doing it with finite difference or the discrete. But yes, you do find that these are different. The values are going to be different. I mean, just like we solve with numerical methods the flow equations and we have some dissipation, we also have some dissipation in the continuous adjoint problem. So we would expect that these values are a little bit different. Now, what you find is that if you look at shape optimization results, or you compare the continuous adjoint and the finite difference gradients, which we have scripts to do, by the way, in SU2, we do this all the time to make sure everything is working okay. You'll find that, you know, if everything is set up correctly, these values are different by small amounts, and either choice is going to be very effective when you're looking at doing shape design or these types of things. So, in fact, I encourage you to take a look at the continuous adjoint.py and finite differences.py scripts. You can go ahead and compare finite difference and continuous adjoint gradients for a particular problem with those two scripts.
Okay. Let's see.
And I want to add one more thing to that.
Yeah.
There's a new development which is coming down the pipeline, which folks may be really interested in. We're just working on trying to get it included. Is an automatically differentiated version of the code. So we have we're going to have the ability here, probably in the near future, to go ahead and have a fully discrete adjoint type version of SU2. So we'll let you guys know much more about that when it's coming. But the plan is to have sensitivities in any manner we can get them. We want to do shape design with SU2. So all of the above. We're an all of the above organization.
Okay. Is it possible to specify the objective function as a combination of variables such as lift over drag?
Yeah, so we do have efficiency. We didn't show that today, but we call it efficiency. It's CL over CD, or lift over drag. And stability as well. We can also use stability as an objective function. And again, just to highlight, if you pop open the config template.cfg file inside the home directory, the root directory of SU2, you're going to find an exhaustive list of a lot of different objectives, constraints, geometric constraints, etc. So they'll all be there for you.
Okay. Right. CPU time for linear elasticity equations.
In terms of specific CPU time, I can't give it to you. Now, in terms of kind of the overall percentage of time for the optimization loop, which I think is more interesting, it's probably on the order of 5%. It's a relatively small amount of time for the full shape design loop. You're spending a lot more time computing the flow in the adjoints. And also we want to note that all of the modules, all of the C++ modules inside of SU2 are fully parallel with MPI. So even the mesh deformation process is fully parallel, which amounts to basically running one implicit iteration in the flow solver. I mean, you're basically setting up an AX equals B system on the entire mesh, and you're just going to solve that one time. So while, yes, the cost relative to some other deformation algorithms, so some people might be familiar with using spring analogies or torsional spring analogies, those can be quite cheap. It is a little more expensive than that because we're solving a PDE, a little more stiff problem. But in terms of the overall process, it's still a small percentage of the shape design loop.
Okay. Let's see. Are you planning to modify the solver to be suitable to run on GPUs?
So, in fact, that's a good question. We are just starting some work now, some new work that is looking at running on either coprocessors, which are similar to GPUs, or GPUs. So we're starting to look at, in particular, a hybrid OpenMP, MPI version of the code. We've already kind of broken ground on this because we realize that kind of heterogeneous computing is the future. So we want to make sure we can extract high performance for massively parallel applications. And we're starting with SU2 EDU. So this is a smaller package that we released earlier this year along with version 3. So this is just a kind of stripped down version of the RAN solver. And what we're doing is taking that and we're trying to strip out all the current MPI stuff, start from scratch, put in OpenMP to work on a single compute node, and then put back in the MPI on top with all the necessary parallel tools in order to have a hybrid OpenMP MPI type implementation. So that's something to look for. We're just breaking ground on that. Hopefully later this year we'll have something to share.
Okay, so would the shape of the far field hex block need to be revisited for a different angle of attack? I think both of us can answer this question. So yeah, there's a number of ways to do that. I think for the problem that we were solving, you know, it probably doesn't need to be revisited. We're a couple of degrees difference. There's a number of ways to kind of either build in an angle of attack into the mesh or via the solver. From the mesh perspective, yes, you could change the angle of the far field hex block to align itself with the angle of attack of the free stream, or you could adjust the angle of attack of the vehicle itself. And by using that inner tet core, again, you have the ability to kind of automate that process if you'd like. Tom, you want to comment on the solver side?
Yeah, I'll just kind of reiterate what you're saying. So it kind of depends what you're doing. So if you're really interested in low boom or boom predictions, low boom design, it will be very important that your cone, your outer region, is aligned with your Mach angle. So, but that's if you're really interested in boom. If you're just interested in taking the original configuration, running at different angles of attack, doing aerodynamic design like we showed today at different angles of attack, the current mesh is suitable. So as a boundary condition, we just impose the angle of attack really at the far field. And so as long as you're kind of imposing that in the configuration file and you're concerned about aerodynamics, the current mesh is just fine. But I would say, yeah, if you're really concerned about boom, you do want to make sure that you have these nice Mach aligned hexes for boom accuracy, accuracy in the boom predictions, etc. But for aerodynamics, you can take the mesh we give you today and change the angle of attack and rerun it, and you'll be just fine. There won't be any issues with the Mach aligned hexes not being aligned anymore in terms of the aerodynamics.
Okay, can you comment on the accuracy of the spatial gradients with respect to spatial directions?
So for I assume you mean the flow variables. So inside the code, we're using one of two methods. We're either using a green Gauss method, which is very typical of an unstructured CFD solver. We also have a weighted least squares method, so to compute the spatial gradients of the flow variables. These are kind of industry standard techniques that are available in most unstructured CFD codes, so we trust them as much as anybody else does.
Okay. Does SU2 have the current capability to output stability derivatives for any included control surfaces on a geometry?
No, not yet, but that's something that we're working on.
Okay.
Yeah, one thing, I'll add one thing to that. One thing we are working on, or at least talking about, is using the FFD boxes to deform control surfaces and rerun simulations. So we're working on some tools that users can implement, that they can put in their config file, so you could deflect control surfaces maybe if you're running multi-point type problems. So that's something we're working on, just to throw that out there. It's related.
Okay. Maybe this is kind of related to that question. So about when you were just talking about the FFD boxes for that. Does the number of control points across the FFD box define the constraints profile for the problem? And if yes, what can we do for defining the spanwise twist constraint for the spanwise location in the FFD box coupled with planform shape optimization?
So I think this is a two-part question. The first thing I want to say is the FFD control point locations are not tied to where we impose any constraints. So if I understood the question correctly, when we have the thickness constraints, the cuts of the sections on the wing, for instance, those are defined separately from the FFD box. So those aren't tied together. You can move those around and do that differently. The second part of the question sounded to me like you're asking how can we impose different types of design variables with the FFD control points, or how can we include more realistic or engineering-like variables. And this is one thing we didn't have time to talk about, but it is a nice feature of the FFD control points, is that you can go ahead and couple those control points into engineering-like variables. So I mentioned camber and thickness. It turns out if you pick a couple of control points above and below the wing and you go ahead and move them together in a combined fashion, you can affect things like thickness if you move them apart. You can make it thicker. If you move them up or down together, you can affect camber. You can also couple large-scale numbers of design variables into wing twist type variables. So if you took the entire box and imposed a twist, so you moved all of the points in concert along some axis, you could impose a twist type variable. And we've done this in the past. Some of these are available directly in the config file. So again, I encourage you to check out the template. And yeah, this is something we we know the FFD control points are great. We also know that a lot of engineers would like to have plan form variables, twist variables, and these types of things. So we're working to support all of those.
Okay. Can the mesh deformation within the optimization handle relatively large changes to the angle of winglets with respect to the wing without creating negative volumes?
Yeah, so I would go ahead and point to the slide I showed early on, where I was demonstrating kind of the volume deformation, the volume mesh deformation. This is one of the reasons we picked the linear elasticity approach. Early on, we were trying to perform, Earlier on, we were trying to perform design using the Rand's equations, and we were finding that near the surface with these small elements, we were having a lot of problems getting negative volumes. Earlier when we were using things like the spring analogy or these algebraic approaches. So we went to the linear elasticity equations for exactly this reason. So we're just going to treat it as a structures problem, basically, and we find that we are able to do this very robustly. So, I mean, you can get a large deformation like we're showing here. I think earlier for the Honor M6 wing, that large deformation of the the tip section, we can go ahead and compute that. And that works just fine. We've also put in some other things for robustness. For instance, we found that if we sometimes break these large deformations into increments, so in the config file we call these nonlinear iterations of the linear elasticity problem. If you step it in increments rather than moving it all the way into place, and you say solve the deformation problem in 5 or 10 steps increments, we can get to some very large deformations. So we found this to be very, very robust, and it's been very good since we put it in. We've done Rand's design and all sorts of things. So it's been quite robust, yeah, to large deformations.
Okay. Would you preserve topology when changing the angle of attack? The answer is yes. With the way that we've elected to construct the volume mesh, we would be preserving the topology because we have an interior tet block and then the hex outer block.
Yeah, and I'll just throw one thing in there, Travis. When you change the angle of attack in SU2, all you're doing is changing the value in the config file, and this just imposes the free stream vector at the far field. So the mesh, the mesh is the mesh. You're just going to impose your angle of attack.
If you were extracting boom at a distance below the aircraft, would you make a sensor there?
So in previous work, we've worked on this quite a bit, and what we typically do is have another surface inside the mesh, which we did not show in this mesh. We didn't, since we were focusing on aerodynamics. We'd often have another kind of a cylindrical surface embedded in that hex region, where that's roughly, 3 or 5 body lengths below the aircraft. And on that surface, we treat it kind of like a boundary condition. We would go ahead and extract a pressure signature right there on that surface. And in the boom prediction work and in the boom design, low boom design type work, that's exactly what we do. And we also have some adjoint capability built into that type of boundary condition as well for doing design, boom shaping. How do you tailor the aircraft to minimize the boom? So that's a whole wonderful problem that we couldn't even get into today. But yeah, we would have another surface embedded in the mesh where we would have a kind of an extraction of the pressure, so a sensor down there, yeah.
Okay. Maybe you could talk a little bit about where people can download the educational version of SU2, because I've got that question a couple of times.
Oh yeah, that's great. So on the URL you see on this page, if you just go to our homepage, su2.stanford.edu, you're going to find a banner at the top for download. Just jump on that page. You're going to find links there to register and download the original, so the full SU2 suite, the EDU suite, and we also have some nice Raspberry Pi binaries that Travis put together for us that are linked there too. So if you go ahead and click on those, you're going to register and download. These are the binaries and the source. You can get the source distribution there as well. And lastly, I'll point out at the bottom of the page, we host the code on GitHub. So if you want to just play with the master, if you want to get on and have live updates day to day, the real deal, latest and greatest, you can just grab the latest copy from GitHub. We have the information right there. No guarantees on that one, though. That one's not necessarily a stable release. So, yeah, that one's actively being worked on. But.
Okay. How does the code scale to many thousands of cores?
So yeah, I mean, for the problem we showed here, it was 100 cores or so. We've run on hundreds of cores. We run on, let's say, order 100 million cell type meshes just fine. You know, one of the things we're going to be pushing to with this new project we're talking about earlier, this hybrid OpenMP MPI implementation, is exactly this. We really want to push the bounds of really scalability and high performance. So we'll have, you know, more about that as we go. But so far we've had no problem scaling to large problem sizes.
Okay. Slide back through here. Do you experience any fluctuations in the sectional pressure coefficient for the shape optimization case because of lack of gradient smoothing?
Pressure fluctuations. So just in the, can you read that one more time, Travis, please?
Yeah, let's see. Is that generally speaking, we are typically experiencing fluctuation in sectional pressure coefficient for the shape optimization in case we are using the Higgs bump function because of lack of gradient smoothing.
We project into the free form deformation box.
Yeah, so I think if I understand the question correctly, one of the things with the continuous adjoint is you may have noticed the surface sensitivities look a little noisy. So if this is on the optimization side of things, what I'll say is we take that surface sensitivity map, which may look a little noisy if that's what the question is getting after, but we always project that into a design space of variables so that we have a smooth gradient to work with in the optimization. So I hope that is answering this question. So we never operate directly with the surface sensitivities during the design process. We always project that into a design space of our FFT control points, for instance, and then use the gradient that we receive from that. So this makes sure that we have a well-behaved flow solution and gradient for the optimization.
Okay. All right, that looks like it's all the questions. Again, thank you all very much for attending the webinar. Like I mentioned, if you have any questions afterwards, please feel free to email me about Pointwise mesh generation, and please email Tom about questions regarding SU2. Again, our email addresses are listed on this slide. So thank you very much, and we'll see you all next time.